So thank you very much for the introduction. So in Aachen we do research on software development tools, and simulators are one of those. And today I would like to present one such simulator. It's called AMVP, an ARM multicore virtual platform that uses parallel SystemC. So first let me quickly introduce what we consider a virtual platform. Essentially a virtual platform is a simulator for a complete microprocessor system, and it's just detailed enough so that it can run unmodified target binary software. And it's intended to be used as a target for debugging, so that when you use it, you will see a GUI just like the one here behind me. You can set breakpoints, you can step the program, investigate registers and memory cells, just as you would do if it was running on the real thing. Now you might ask, like, when it's looking like the real thing, why just not use a physical platform instead of a virtual platform? And the reason for that is that the virtual platform has a set of advantages that we want to exploit. Well, first of all, it's usually available quite early in the development cycle of a new project. So we have tools that allow us to assemble virtual platforms very quickly, so software development can start quite early and even concurrently to the hardware development. And it enables a feedback channel between the software and the hardware developers, which is advantageous. Secondly, if you have a virtual platform, it's very easy to redistribute it to your developers. It's basically just a software package that you can copy to every host machine, and it's much easier than if you have like a single physical prototype that you need to share, possibly among different sites. And the last advantage that's important is that since it's a software simulation, we can pause and stop it at any time. We can look at every component in the simulation, every register, every memory cell completely non-intrusively. So for bugs, it's very difficult to hide from us in a virtual platform. Now, VPs today are usually built using SystemC, which is a C/C++ library that contains classes and tools that are useful when modeling hardware. Its C++ nature usually guarantees us that it compiles to very fast running code, and it allows us to incorporate hardware behavioral models, for example, instruction set simulators, into our virtual platforms, since those are typically also written in C or C++. Now, so that's all nice, but what's the problem? The problem is performance. A virtual platform can never run fast enough. So to introduce a baseline, I would like to present a very simple virtual platform that I've created with an in-house written instruction set simulator that uses regular SystemC and then boots into Linux and executes a parallel version of Drystone. And then I measure performance. In a virtual platform, we measure performance in terms of MIPS, millions of simulated instructions per real-time wall clock second. And using this small example, I got this performance. So in a single core configuration with just a single ISS, I get 36 MIPS, which is fine. But when I go to a dual core system, the performance halves. And in a quad core system, it halves again. And the reason for that is that the underlying simulation engine, i.e. SystemC, only uses a single thread to drive the entire simulation. That means if you have 4 times the processors, they each need to share time, so each only gets 1/4 of the time in simulation. And that means you experience a reduction in simulation speed, since now in order to reach your breakpoint, it takes 4 times longer. So this is the starting point from which I went, and I wanted to basically achieve 2 things. First of all, it would be nice to have a simulator that already runs faster than 36 MIPS in a single core configuration. And I wanted to use parallel simulation or parallel SystemC to kind of counter the performance degradation that I saw once I went into multi-core systems. So I started looking at QEMU. It's proven to be working. It works very nice. It simulates all of the various ARM instruction sets. We know it boots Linux and Android, so it can be used as a golden reference. And it's open source. So if something is not to our liking, then we can easily change it. Now, looking further, this is not by a long shot the only approach that couples SystemC and QEMU. There have been many in the past. So for example, the conventional approach is to have QEMU running in one process and your SystemC model in another, and you communicate using IPC, which is unfortunately kind of slow. Combining it all into one process is done by our colleagues at Weinstock. So they use QEMU as a slave component within a SystemC simulation, but they only target single core systems, which is not so interesting for our research. So the next idea was then to basically go with their approach, but have QEMU simulate actually multiple cores within a single instance of QEMU, which would be similar to what you can get when you're using ARM fast models. But then again, this is only suitable to build HMP or SMP designs, which in research is probably not so interesting because you maybe want to be more flexible. And that's how the idea for this work came up. So what we want to use is we want to have one SystemC simulator that uses multiple copies of QEMU, each wrapping a single instance of your ARM cores, and then you want to be able to interconnect it however you want, like a single bus or a NOC or not at all, basically what you want. So how did we go about this? Well, first of all, QEMU is a standalone executable that can't remain the same, so it's getting converted into a shared library. Next, we want to be able to have multiple copies of QEMU, so we must take precautions so that we can actually instantiate multiple copies of QEMU. That means replicating all global state. Global state is basically your processor registers, etc. Fortunately, on Linux, we can use DLM open to use the binary to load the binary into its own namespace that simplifies the process. And then we must make sure that all of the copies are self-sustained. They cannot have any external references, or otherwise we would risk race conditions during parallel simulation, and that could lead to functional faults. We want to have everything inside a single global memory address space because that allows us to model loads and stores efficiently just by using mem copies. So the fundamental structure is like this. We have one process, and inside this process memory there lives our models. There's like our simulation library sitting somewhere, our UART model, our bus model, and then there's our processor model. The processor model uses DLM open, once we instantiate it, to create a copy of QEMU in memory, which is fully self-sustained as indicated here. When we want to have a dual-core system, we just create a second instance of our processor, and QEMU gets loaded a second time into memory using said DLM open call. Now that's about the plan, but now we also said that we wanted to have parallel simulation. So in the past in Aachen we did some research on parallel SystemC. We have our parallel SystemC kernels there. But I had also another idea, because QEMU is kind of already running in its own thread, so there might be a simpler approach to achieving parallel simulation. And I did this by creating a new component which I called thread control. Basically how it works, SystemC internally controls the QEMU instance just using this thread control mechanism. And thread control basically sends simple commands to QEMU like run or step or stop or whatever to control simulation. The nice thing about this is that this thread control component, it's much simpler than having a full parallel SystemC kernel. A full parallel SystemC kernel is like around 40,000 lines of code which you need to maintain, whereas the thread control component is only around 3,000. You still have to maintain your SystemC kernel, but this is done, for example, by Accelera or Synopsys, wherever you get your kernel from. Now, how does the parallel simulation work? Well, as I already said, SystemC needs one thread for XF, and then we have one thread for each instance of QEMU in our simulation. I'm switching here to a quad-core example. So SystemC starts running, setting up the simulation, and at one point in time, we want to drive the simulation of the processors forward. So it sends a message, a command to run to each of the cores present in the system, and they, in parallel, start executing their quantum. We don't simulate individual instructions, that would be too slow. We group instructions to bundles of around 1,000, maybe 10,000, and execute them at once. Once everyone has completed, we report back to the kernel, time gets advanced to the next timestamp, and the whole process continues. All the four instructions, all the four ISSs execute at the same time again. And this continues like a normal discrete event simulation would do. Now, is this enough to build a parallel simulator? Well, it turns out, unfortunately, no, because there's exclusive memory access, basically atomic memory access. Because by introducing concurrency or parallelism into our simulator, these atomic instructions must now not only execute atomically in simulation time, but also in real time, since there might be races between the different instruction set simulators. Now, the tricky thing is that ARM uses a completely different approach to what Intel does. Basically, some instructions that are called load exclusive and store exclusive, and how you can build an regular atomic instruction using those two instructions is just exemplified here. The challenge here is, as I said, that Intel does not have a good representation of load and store exclusive, only atomic, compare, and swap. So we needed to find a way around that. One approach would be to just trace every instruction, everything that goes into memory, and decide whether a store exclusive should go through or not. The problem is that this is a serialization point and completely kills performance, so this is out. The next option was to just model it as good as possible using cars. And we did this like the following. So when we do a load link, we just remember the data that we saw at that address, and we only do the store when the value in the set memory address has not changed. Of course, assuming that because it still has the same value, it hasn't been changed in the meantime is wrong, and there's like, for example, the ABA problem. But we found out that in the software that we are running, for example, Linux kernel or C libraries, we can guarantee that the values stored are unique. So there can never be ABA, only ABC. So we circumvented this issue. So just to give a high-level view of the system that we built. So there is a quad-core system connected to a shared bus, a generic SMP approach because we wanted to simulate Linux on top of that. So each of the blue boxes here represents one instruction set simulator that wraps QEMU. There's a generic interrupt controller model that, because of the time, I cannot go into detail, but basically it handles inter-processor communication on the SystemC level. And then we have some virtual I/O, like some UARTs and Ethernet MAC that you can use to go online with the virtual platform, some SPI, etc. This thing is detailed enough to boot Linux and Drystone. So let's look at the simulation performance. So first of all, I was interested in the sequential performance. So I make the constraint that only one thread can be active at any given point in time. And the first benchmark that I'm running is Drystone. In a quad-core configuration, I place 4 copies of Drystone in memory, and each core runs on its own. And then I measure the runtime to complete, I think, 4 million runs. And you can see the result here. If we have a small quantum of around 1 microsecond, it takes really long. It actually times out, so I didn't bother to look into that anymore. But around 100 microseconds, we're actually reaching a point where it gets reasonably fast. Now let's convert that into the MIPS number by just counting the instructions. And that you can see that we are already a lot faster than we were at the beginning, because like at, again, 100 microseconds, we reach almost 100 MIPS. So moving on to look into something that is less computational, I decided to check out SMP Linux boot. So basically it simulates Linux from power on until you get presented a locked-in shell. And as you can see here, the trend is the same. The bigger you make your quantum, the shorter the runtime gets, which is intuitive because it means less synchronization and therefore higher performance. However, if we convert that into actual MIPS numbers, these are a lot lower than before. Well, the reason for that is that Drystone previously just really did some computation in memory and didn't use SystemC or any of the components at all. And Linux now really activates the generic interrupt controller, the UARTs, etc. So the simulation spends a lot more time in simulating the other hardware than it does executing instructions. And furthermore, also Linux is a really control flow dominated stuff, which, well, QEMU just runs a little bit slower. Following that, I wanted to look at the parallel performance. So I'm lifting this constraint now, and all threads may run in parallel. And I'm looking again at the runtime. So here are the 79 seconds for Drystone that we got before. And here you can see the runtime using the parallel quantum with the thread control approach. And you can see it's already about 2.5x faster. For your reference, I've also done a measurement with a fully parallelized SystemC kernel. It's a little bit faster. It reaches 2.8x because it can, of course, parallelize a little bit also of the internals of SystemC, so it has an advantage there. But since the instruction set simulators really are the major part in the simulation, already with a parallel quantum, you reach like a really reasonable number. The same data for the Linux boot. So with the sequential performance, we were reaching the log-in shell after 32 seconds. With a parallel quantum, we are there at about 12 seconds. We reach a speed up of 2.6x due to parallel simulation and 3.2x when we use a fully blown SystemC kernel. So what does it tell us? So first of all, we were able to construct a virtual platform that is detailed enough to boot Linux on ARM, even SMP Linux. And it's really fast for computational workloads like Drystone, given that it has enough of a free leash, like a big enough quantum. And of course, we're using QEMU. It's actually really easy to retarget it to support ARMv8. We're actually currently in the process of finishing that work up. It basically just leaves the load and store instructions that we need to handle. Now, the important thing I also wanted to look at is the parallel operation. So I've shown you that we achieved like 2.5x, 3.2x speed up there, and here are some more detailed numbers that puts this into context. Of course, like a fully blown parallel SystemC kernel, like the scope kernel here, achieves a little bit better results, I admit that. But I'm actually pretty proud of this parallel quantum approach because it's like so simple, it reduces a lot of complexity, but still achieves competitive results. And I think like eliminating this need for this complexity is always a good thing. So to close, I really want to make just a statement that if we want to keep our virtual platforms useful as software development tools, we have to keep them fast. And in an age where we're just basically only considering multiprocessor systems, we really need to do something about the performance degradation that they suffer. And I think that the parallel simulation is at least one viable approach that we should use to keep our simulators fast. And for that, if you're, for example, in the business of making instruction set simulators, you should really think about keeping them thread safe to make the work of the virtual platform designers a bit easier. So that's it. Thank you very much.
So, any questions? Okay, I have one. So, when you split your QEMU threads into separate QEMU, cores into separate QEMU threads, where does your cache sit, and how do you deal with the cache coherence between those different cores?
So, short answer is we don't model cache, because from the point of view from the programmer, a cache is invisible. The only way you can detect that there's a cache is that you do timing analysis, right? You measure the access time of data in memory, and we can get this information by other means. So there's no like model of the cache with the cache line. All of our data immediately goes to the cache to the main memory. So you could actually create like a second processor that has no access to the caches of the first processor, and it would still see all of the original data in memory. That's just a decision. We don't want to model that because it's too slow to model it. But what we can do is we can of course model the timing. But even if we do that, you would still notice that we are taking a shortcut there.
Okay, well, the upside is, of course, you're then inspector free. Okay. Any others?
I'm curious to know, you mentioned that you ran multiple copies of Drystone. Did you model any synchronization effects on performance by running a workload with shared memory?
I did not. I basically used a scattered version of Drystone. That means the application gets just loaded 4 times into memory at completely separate locations. They don't talk to each other. There's no synchronization necessary. It's basically an ideal example to represent the upper limit of what's possible. Not only because there's no synchronization, but also because Drystone essentially is a loop. So the QEMU instance will obviously be very fast, since it recompiles the code once to x86 and then can always reuse it. For that case, the Linux example is much better, because there you have a lot of crosstalk between the cores. A lot of cores do different things during the boot time, and that's a more stronger test that represents the synchronization, which you don't have in Drystone.